Hey there. Let me start with saying what is Zorabots. Zorabots is a robotics company. It's short for Zora Robotics. It was founded in 2011, and the focus is on making robotics accessible to all. It started really simple with a TV remote um, controlling the Now robot, the one you see on this slide, and it evolved into a crazy operating system called ZBOS. Now, what is ZBOS? ZBOS is the Zorabots operating system. We started working on it back in 2017. And well, it was based on all the prior work, of course, but it was a completely new system meant to be universal, cross-platform. And well, you can compare it to like a Windows for robotics, basically. So there's an Android, Java virtual machine, and a web version via Kotlin multi-platform. These are most of our robots that we support. You have Cruiser here, Pepper, James, the small one is Robin, then now that you saw the first slide. Billy, which is an interactive flower pot. Aimbot helps with the pandemic, and Sawyer is a big robotic arm. We also support virtually any Android device, and we have a version running on the web with virtual robots. You see the virtual Zora there in a virtual home. You'll have a control application which works on your phone or on the web. It allows you to control your robot, the virtual robot, or an actual robot. This is the website if you want to check it out. And everything runs on a single API. That's what we're here for today. So our API is based on MQTT. There's a broker on the robot and a broker on the cloud. It's rather huge considering it's 600 channels across 26 categories. And I hear a lot of people in the AsyncAPI development are using it for benchmarking things because it's so huge. So that's quite funny. You can see our documentation on the link below.
So essentially, we have two brokers running, MQTT brokers, one on the robots, which you can see on the left here, and one in the cloud. These two brokers sync each other, and we mainly made one in the cloud so we could remotely access the robots through our control app. Since we access and control the robots through an MQTT API, that also means that third parties can integrate to it. You can either run an app on the robot itself and connect to MQTT, or you could even have an external app running somewhere, for example, on an IoT device, something maybe that monitors the air quality and then reports it to the robot or stuff like that. These are some examples of our API of our topics. For example, what we do a lot is we have a publish topic to request something. In this case, we do a battery gets because we want to get the current battery state. And then below it, you see the response. We always work with passing a key in the payload, and then the response contains that key, so you know that the response is for you. Since it's a broadcast system, you have to do something like that. And the payload is mostly are JSONs. For example, in this case, you get your battery level and percentage. You know if it's charging or not, and you know if it's docked or not. Because we don't want to poll to for the battery state, you can also listen to the battery event topic, which does the same as the response, but publishes it's once in a while every time it changes. So that's just one example. We have a lot of topics. You can control movements, you can play audio or set of volume levels. You can open a camera stream, take a picture, turn on the lights, change the color of the lights if the robot support it. You can play media, play audio, or show videos on or images on the screen if the robot has a screen. You can let robots say something through text-to-speech, which we support for multiple languages. You can listen to sensors. Some robots have like bumpers or buttons which can listen to, and also motion detection and face recognition through the built-in cameras, or listen to a voice command. If a person says something to the robots, you can then do something. So we also support automations. We have through our control, we have a composer system where you can essentially place blocks. Think Scratch or Node-RED, but specifically made for ZBOS. And we also have a scheduler, so you can start automations on specific time points. We also integrate domotics through Home Assistants. So Home Assistant publishes data to our robot, and you can act on it. We also support third-party apps. They can integrate into ZBOS by, for example, adding themselves as an app. They can register themselves as an app, so the user can see the app visible on when he fetches all the apps and control. You can add settings which the users can then change, custom translations. You can add monitoring if you have a monitoring device, for example, a CO2 meter or something like that. Then, as we have an extensive API, we surely had to document it. In the early days, we just updated a page on Confluence where we had a list of all topics and a description of them, what payload had to be sent in it. Of course, it was hard to maintain. It had to be updated every time we changed something in code. It was always out of sync, and it contradicted the actual code. Also, it wasn't easy for third parties to read out the API. So we started using AsyncAPI. So at first we just made manually we made a YAML file where we put in all the topics and payloads and stuff. It was quite easy to maintain, but all developers had to learn the AsyncAPI syntax because they had to update the documentation every time they changed something in the code. And it happened that something was forgotten and it was still out of sync. So what we essentially did was we made multiple YAML files per category, and then we used the YAML Inc. Tool to sync those files or merge those files into one big one, which we then published. So we wanted to make that progress better. We wanted to automatically generate the documentation. So we went one step further and we let the AsyncAPI file generate from code. So it was at that point it was easy to maintain because we didn't have to manually update it. The code and documentation was always in sync, and we because we generated the code file from code, we didn't need to make any code changes. We didn't need to change your data classes or something like that. Downside is we need a lot of annotations in our code because we had to say, okay, this topic has this description, so we had to annotate that, and we had to add some custom code to make this all work. And And it doesn't always form the nicest docs. Sometimes you can make a more proper doc when you manually make it, but we found it wasn't that big of an issue. So why did we decide to essentially work on a code-driven way? So in a perfect world, we could have just made an async API and then let our Kotlin code generate from that. For example, we could have defined a battery event in an async API, and we could then export it to a Kotlin class, and it would look something like this. For example, we would have our battery event with a level, if it's charging or not, if it's docked or not. Of course, that's not how the real world works, I'm afraid, because our data classes aren't that easy. We had, for example, to add some annotations. We had to add serializable annotation for our JSON parser. We had to add the JS export annotation because we wanted to make the data class available from JavaScript for our Kotlin multi-platform integration. Some other problems, again, we had some annotations like the serial name. JSON parser, which says Kotlin multi-platform, doesn't automatically convert camel case to snake case. So we had to add serial names. Sometimes we had our functions in the data class itself. For example, this one, if the request is valid or not. Or for example, these ones where we made some helper functions. If you get a jar and it's null, then instead return 0. So we could work around it, but that would mean we had to do a lot of code changes. Some classes I don't think we would be able to work around. For example, we have an enum here, which we give a parameter to. We have a custom serializer, which is also added to an annotation. And because some bug in Kotlin, we also had to add a companion object to make that serializer work. So this would be hard to generate from a AsyncAPI spec file. So that's why we chose to generate the AsyncAPI file from the code. So how do we do it? We essentially have a Kotlin MQTT library where all our MQTT topics and data classes are defined. And we made a generator, a AsyncAPI generator app or library, if you will, that integrates that and then generates an AsyncAPI JSON file from it. For that, we made use of the JAsyncAPI library, the link you can find there. How does that work? Well, essentially, you can define an AsyncAPI and encode instead how you would normally do in a YAML or JSON file. So, for example, below in the code, we would create a ZBOS MQTT API class, and then we would serialize it to JSON and then return to a file. So how does an MQTT API or an Async API class look like? So here on the right, you can see we have a class that extends the Async API class, which comes from the library. And there we have to override some implement some functions. For example, the getInfo function requires you to return an info object, which you can find on the left side of the screen, which you just fill in with some metadata you normally find in an Async API file. For example, the title, the description of the API, contact information, the version, stuff like that. The same is essentially done for other things like servers or all available tags. However, it's the components part that we wanted to, the channels part that we wanted to automate. what we did is we made separate classes where we grouped some of our MQTT topics. For example, we have here the battery channels class, and there we return, I'll go to the code the next few slides, but we generate some publish and subscribe topics, and we pass our MQTT topics, which we already had in the library. So we create a publish here for battery gets, a subscribe for battery response, and a subscribe for battery events. So what is that constant? For example, we have the event. So the battery event I mentioned on the previous slide is here. It's just a static string. The static string is used in multiple of our projects where we pull in that Kotlin library, and we then consume those constants to do our subscribes and publishes. But we had to add extra information, of course, to make sure we could generate AsyncAPI docs from it. So we opted to add annotations to each constant. So for example, we would have the add topic summary annotation, which would then add the summary, and the AsyncAPI docs, the description, and then the data where you would pass a class in. The class is the payload you would send typically for that topic. So in the class itself, we also added some annotations. For example, if you wanted to add a description to a property, you could add it by using add property description. Or we also made some small helper annotations. For example, the property schema, which you could then add, okay, this is percentage, the level of a battery is percentage, and it would then automatically generate the minimum is 0, the maximum is 100, add a description to it, stuff like that. So you didn't have to add it every time you had a percentage property in a class. So how do we process those annotations? We use reflection for that. So we in Kotlin you can get the properties of a class or of a field, and then you can get annotation from it, and then get the data in that annotation. These are 3 examples: the summary, description, and the data class. Now these methods that I just mentioned, you can then call. We would by using the AsyncAPI library, we would build an operation and then add the summary, description, and message to it, and we just get the information from the annotation from it. The message, so the payload required some extra code because that's more complex, and it's a simplified version looks something like this. So you would build a schema, and in that schema you wanted to set the properties. The properties are then retrieved from the primary constructor of a Kotlin class, which is essentially the constructor, the only constructor a data class normally has in Kotlin. Then we would loop overall parameters in it in the constructor. We will check what type it is. We will check if it has annotations and get those, and fill the information in as well. If we see that the type of that property is not a string or an integer or something like that, we would, but it's an object, we would then recurse and get properties from that one. So we would have a nice tree in the schema. Of course, more had to be done. For example, the serial names we used for our serialization, we had to use those ones instead of the camel-cased names we used in the code itself. We also had some non-constructor fields in some places we had to add. We had to add some special handling for arrays and enums and objects. We also had to prevent infinite nesting. Sometimes a property in a class has the same class as the class itself, so it would just keep looping and have an infinite nested code. So of course that's we had to break up, and there are some other cases as well. The only thing we still added manually is examples. We weren't able to add those through annotations, but we just added them, and after we generated the AsyncAPI schema, we just added an example for example, battery event, then level, and all the properties filled in. So it would show up nicely as an example in the AsyncAPI documentation. The outputs from that library is then one big JSON file, essentially containing all topics, but we also opted to create a JSON file for each category separately. The reason we did that is because we wanted in our web portal, in the documentation portal, we wanted to split up everything into separate categories, and then load one of those JSON files depending on the selected category. Showing one big page wasn't user-friendly and not performant either, so we opted to do that. The big JSON file mainly exists for third parties who just want to integrate everything while they can use that file. So it's also integrated into our CI/CD. Every master build we do, we run the code to generate the documentation, and it's then published to our public Git repo. So that means it's available immediately every time we do a release. And it's also tagged with the version that we released at that point. It's also integrated into our documentation portal. And Wim will give more information about that.
Thanks, Davey. So what we see here on this page is our documentation portal. On the left-hand side, you see all the categories in our API. On the right-hand side, you see all the topics you can subscribe or publish on. And of course, the details in the center. You can find this site on docs.zorabots.be. Everything is built with Antora. Antora is open source documentation tool. And all documentation in it is written in AsciiDoc. AsciiDoc is like Markdown or other markup languages, except that it's quite advanced to make structured documents, so it's perfect for manuals and technical writing. What it does basically is aggregate documentation from multiple sources. As our documentation, our AsyncAPI API is just published to a Git repo as well. We use the tools created by David Jenks to convert it to AsciiDoc and then integrate it into our doc portal. It's really nice because it also generates the navigation and all the cross links between different topics. So it's a really nice tool. We also consume our own async API in the ZBOS Control application. So there's an MQTT block, like a building block in our programming environment, where you can publish and subscribe to topics. You can connects to multiple MQTT brokers if you like. So this is how it looks basically. All the topics that are in our API can be searched easily. So as you can see in this list, if you click the information icon, you get some more information about this topic. All those things are rendered from the AsyncAPI spec. And then if you select to use one of these things, it ends up in the block and you can change the payload if you like. In this case, you are checking the battery status of a robot. As for future plans, we've been working a lot on a virtual environment and virtual robots the past year. And I would say that 95% of what we've been doing is not even live yet. So 2022 looks really nice when it comes to releases. We want to further expand on our Composer application because there's a lot of opportunities in education, especially because everybody knows robots are expensive. And if you can have a virtual robot that does all the same, it's perfect for STEM classes and stuff like that. So our focus will continue on virtual robotics as well, as it's just all the same codes as for the real robots. And part of that is building a community of people where they can share their own compositions, as we call them. So they can share their own programs they make with our software and improve upon it. And another step there is to allow third-party integrators to easily interact with our system, make their own composer blocks, which are like the fundamental building blocks of our system. So these are the things that in 2022 we are really looking forward to. If you are interested in more of that, I set up a mailing list. You can subscribe to it. We can give you a free trial to our virtual robot platform the moment we launch it. So please do. Don't worry, we won't spam you with anything else. This is basically, I made this list just for this presentation. If you like what you heard and you want to participate in our projects, please feel free to reach out on jobs@zorabots.be. Thank you very much for your attention. If there's any more questions, me and Davey will be there just after this. Thanks.